Hi, in this next unit, we're going to start using numbers in chemistry, but I really don't want you to worry about this at all because it's a lot of just multiplying and dividing. Occasionally, we might add or subtract. So, the thing we need to learn is about how to use numbers in science properly. Now, this video will apply to chemistry, to physics, maybe to your life sciences, anytime you use numbers in science or experiments. So there are two kinds of numbers. There are exact numbers, and these are numbers where their values are known exactly. And there are inexact numbers, and these are values that have uncertainty. Exact numbers are defined numbers, like there are 12 eggs in a dozen. That 12 is an exact number. Or some definitions, like there are 1,000 grams in a kilogram. Or if you're counting something, like 24 students in a class. Again, their value is known exactly. Inexact numbers are generated from measurements, and measurements are going to be inexact because maybe the instrumentation isn't exact. There can be human error in reading the instrumentation, but all measurements, no matter what, are inexact numbers because there is some uncertainty and there is some error. So here are some vocabulary words. So uncertainty is how we express how sure we are that the measurement is truly what we say it is. And a lot of times you may see this when they have that plus minus notation. For example, here at the bottom, it says you take a measurement and you say it's 1.58 centimeters plus or minus 0.01 centimeters, which means it could be 1.57 to 1.59. But in science, we just wind up dropping that plus and minus notation and knowing that the last number that is recorded has some uncertainty in it. Okay, accuracy. We need to know this definition. The correctness of a single measurement. The correctness of one measurement. So it's determined by comparing what you measure against the accepted value. Sometimes people call it the true value. And then precision, we need to know this one. This is how well experimental values agree with one another. Okay, so let's go back. Let's look at accuracy is the correctness of a single measurement, one measurement. Precision is when we're seeing how values agree with one another. Okay, so precision, it's about consistency or how you can reproduce your result. So usually the more decimal places that agree, that means the more precise you are. Okay, so here's a balance like we have in the lab, and we're going to be using them a lot this semester. And if you were to weigh a raisin with one of our balances, it would give you 1.2 grams. If you weigh it again, it would be 1.2 grams. But if we use the analytical balance in our lab and we put a raisin on there, it would weigh 1.235 grams. We know more precisely using the analytical balance. It gives you more decimal places. Okay, let's compare accuracy and precision. All right. We're going to say that the bullseye on this target is what is the true value or the accepted value. So in that dartboard, nobody's close to the bullseye, so nothing is accurate. And the darts are not close to one another, so nobody is precise. In B, nobody hit the bullseye, nobody was accurate. However, the darts are close to one another, so they are precise, they're reproducible. Okay, and the next one, they're pretty close to the bullseye, but they're not close to one another. So we would say that there's high accuracy, but low precision. And on dartboard D, they're in the bullseye, that's a high accuracy, and the darts are close to one another, high precision. All right, now this is important, and you're going to hear about this a lot. Excuse me. It's significant figures. Some teachers will call them sig figs. Some teachers will call them significant digits, but whatever it is, they're all the same. It's all the digits in a measurement that you're sure of, plus one digit that is estimated. It's a way to express precision. The more sig figs you have, the more precise. So let's count our sig figs. 1.85040. Woo, that's a precise measurement here. All right, we always count from left to right. You start counting the first non-zero digit. Okay, so that would be the 1. All right, if there's a decimal point written, you count all the digits after the decimal. If there's no decimal point written, you do not count the trailing zeros. So in this top number, 1.85040, all of those numbers are significant, even that last 0, because there's a decimal point written. So how many sig figs are in this top number? In this top number, 1.85040, there would be 6 significant figures. Now look at this bottom number down here. It's the same set of numbers, however, there's no decimal point, so the magnitude is very different, and we will not be able to count that last 0 because there's no decimal point written. So there would only be 5 significant digits in that number. Okay, so let's practice. How many sig figs in 0.009? Okay, never ever count the zeros at the beginning of a number. They don't count. They just are holding the decimal place. So in the very first one, right here, let's see. Let's go back. In this one, there would be 1 sig fig. Okay, here, these zeros do not count. They're at the beginning of the number. This 9 is significant, and these trailing zeros count because they're after a decimal point. So that would have 3 significant figures. Here, 114,000. These trailing zeros do not count because there's no decimal point. So there's only 3 sig figs here. The 1, and the 4 are significant, but these trailing zeros, they only count if you have a decimal point in your number. Here we have 114,000, and then there's that decimal point. That looks weird, but what that does is it makes all of these trailing zeros significant. Okay, so let's summarize. All non-zero digits are significant. So any number 1 through 9, significant. If you have zeros in the front before you ever have another digit, they're never significant. Zeros at the end of a number only count if you have a decimal point in your number. We're going to practice this in class as well. So you may be asked, how many sig figs are in this number? Okay, so now what do we do with measurements and calculations in sig figs? That's what we're going to find out in our next